Okay, so we're back with our relations and our domains and ranges. And what we want to be able to do in this video, or by the end of this video at least, is to represent our relations visually in some way. Okay, we already saw how to do that kind of in the first video on this topic. And one of those ways is to draw a graph of your relation. All right, so let's do an example. Let's say I've got relation B, and it is equal to the set of all ordered pairs x and y, such that my y value is equal to x plus 1, and my x values can be taken from anywhere in the set of 1, 2, 3, and 4. Okay, so that's my relation B. We can write this another way, and you might recognize this from the previous video. This is just a set of ordered pairs 1, 2, 2, 3, 3, 4, and 4, 5. Okay, so we've got 4 pairs of coordinates. That's pretty easy to draw on a graph. So let's do that off the side here. Okay, so we've got 1, 2, 3, 4, 1, 2, 3, 4, 5, and you just plot those points in. Okay, so 1, 2 would be here, 2, 3 would be here, 3, 4 would be here, and 4, 5 would be somewhere there. Okay, notice they make a straight line. But the key thing here is you don't fill it in with a line. Okay, because this relation is only talking about 4 specific points, you must only put those 4 specific points on your graph, okay, and nothing else. And that's it. There you go. You've represented this relation visually with a graph of some kind. Let's do something similar, but using a relation containing an infinite amount of ordered pairs or an infinite amount of coordinates. So we'll go and write D. Well, D will be the relation defined as all the ordered pairs x and y, again such that the y value is the x value plus 1, and here we'll say that x can be any real number we like. Okay, positive, negative, 0, rational, irrational, doesn't matter. Okay, all right, now you can't write out a list of all of these ordered pairs because there's so many, there's infinitely many of them. You'll be there forever, literally. Okay, but we can get a sense of what it's going to look like. All right, all we know is basically that the y value is just going to be 1 plus the x value. Okay, so if I go ahead and look at, say, an x value of 1, I know that the corresponding y value will be a 2, because that's what my rule says, y equals x plus 1. So I'll get a point there. All right, I could choose the point 1.5. Okay, might be somewhere there. And I know that the x coordinate will be at 2.5, which will be somewhere there. All right, now the point here is that you can populate the Cartesian plane with points using any x value you like. Okay, so in between these 2 points that I've already got here, there are actually infinitely many other points that we could plot in. And you could keep zooming in and zooming in and zooming in and filling in all the gaps with even more coordinates, okay? And you can do that all along your x-axis. And what you will produce is basically a graph of the line y equals x plus 1, okay? So that's going to have a y intercept of 1 and an x-intercept of negative 1. All right, and the point here is that this line goes on forever in both directions. All right, and every single possible gap between any 2 coordinates on this line is filled in with an infinite amount of other coordinates. Okay, and the end result is basically just a solid line. Okay, there are no gaps in this line because that gap could just be filled in by choosing an appropriate x value. So there you go. Okay, so the graph of a relation such as this is simply just a straight line, a normal straight line that you're used to graphing. Okay, y equals x plus 1. You could do the same thing for y equals negative 2x minus 3, negative 7x plus a billion. Okay, it doesn't really matter. The point is that it's a solid line because every single x value can be used to generate a coordinate or a point. Okay. All right. Now let's go quickly and talk about domains and ranges and see how they relate to the graphs that we've drawn here. Okay. So, I mean, the domain of set B is just the set of all the x values. That's pretty easy. 1, 2, 3, and 4. So I can say that the domain of B, is 1, 2, 3, and 4. And likewise, you can look at the range of B. Because those coordinates are listed out for you, you can just read them off and list them down. 2, 3, 4, 5. Easy peasy, okay? Now, for something like D, okay, if you saw the previous video, it's a bit hard to think about what the range is and give an argument for that. But there's a really easy way to sort of visualize and think about what domains and ranges are, okay? So let's look at our graph. And what you want to ask yourself is, what is the set of x values for which my graph has been drawn? Okay, so can I say that the graph is drawn for an x value of 0? Yes, that's up here. That's at the y-intercept. All right, is my graph drawn for an x value of 1? Yep, that's here. 1.5? Yep, that's here. Okay, 10? Yep, that'll be somewhere up here. A billion? Yep, that'll be all the way off the screen somewhere. But the point is, your graph will be drawn if you choose that x value. And you can choose any x value you like. Okay, so the graph is drawn for all x values. That's what that means here. Okay, all x values are used to draw this graph. So that's your domain. And we already know this. Okay, we already said that that part of your relation rule describes what your domain is. Okay, the harder one to think about though is the range. What is the range of D? Well, you just replace the letter x with the letter y and you ask yourself the question, for what y values is my graph drawn? Okay, notice the lowest possible y value, well, that goes off the screen. That's all the way down at negative infinity. And any y value from negative infinity up to at least 0, you can find a corresponding point on your graph that's been drawn. And you can keep going up and up and up your y-axis forever, however far you want to go, all the way up to positive infinity. All you have to do is go across and find the point on your graph that corresponds to that y coordinate, okay? So any y coordinate you choose, your graph is going to be drawn for that y coordinate, okay? So that's why the range is also R. All right, now here's another way to think about the definitions of the domain and range, kind of what we were talking about here with the graphs. Okay, and this is how I want you to think about it. So the domain is the set of all x values that have a corresponding y value. Okay, or another way, in other words, that's just saying the set of all x values for which a point on your graph exists. Okay, because if a point on your graph exists, then there is a corresponding y coordinate for your x coordinate. Okay, the range, exactly the same statement, just swap the x and y. So the set of all y values that have a corresponding x value. Okay, and again, in other words, if you choose a y value and you try and find the corresponding point on your graph, then if for a point to exist, it must have a corresponding x value. Okay, and you'll notice that any y value you choose for this graph of D, you will have a corresponding point and thus a corresponding x value. And because no matter what value of y you choose, that will happen, the range is going to be all real numbers. Okay, so that's how you want to start thinking about your domains and ranges. For what values of x and y are my graph drawn? Okay, does my graph exist? All right, so that's using graphs to visualize relations. There is another way to visualize. It's less common. You'll see it pop up from time to time, but it's not really, a good way to sort of visualize the relations between x and y, especially if you've got infinitely large relations. So again, let's say I've got the set B, and that's going to be 1, 2, 2, 3, 3, 4, and 4, 5. Okay, what we can do here is I can write down all the numbers in my domain. So 1, 2, 3, and 4. All right, so that is the domain of B. I can write down all the numbers in my range. So that's going to be 2, 3, 4, and 5. So that's the range of B. And all I'm going to do is one at a time, ordered pair by ordered pair, just draw an arrow from the x value to the y value. So for the first one, we've got x value of 1, y value of 2. So I draw an arrow from 1 pointing to 2. The next one, 2 to 3. So it goes across like that. 3 to 4 and 4 to 5. Okay, this is called an arrow diagram. Again, you can see how tedious this would get the larger and larger your relation gets in terms of the number of coordinates it has. Okay, so it's only really useful for sets that have small numbers of coordinates. That's an arrow diagram. Okay, so you might see that term pop up and they might ask you to do a representation of your relation using that way, but most of the time you're drawing graphs of your relations to visualize them. Okay. Anyway, we'll stop there. So next time we'll start talking about functions, which are very special types of relations, and properties of functions. All right, see you then.